All right, and welcome to part 2 of chapter 17, Acids and Bases. So where we left off was pH and pOH, where we used a log transform to take something with a really broad range, which is the concentration of protons or the concentration of hydroxide ions, and converted it into something that's simpler to assess visually, something we have a little bit more intuition for. So pH is just a negative log scale of the concentration of either protons, or protons for pH and for pOH, hydroxides. And you've probably noticed that there's a large range for K values as well. They can be very, very large, or very, very small, everywhere in between. And because of this, this also lends itself to being corrected with a negative log transform. And when we do this, it's called the pK. So we have the pKa, which is for acids, and pKb, which is for base. And typically we interact with the pKa because you can always calculate pKb based on pKa. So most tables you see are going to be for pKa, but it's good to know both and be able to go back and forth between both. So pK is just another way of describing relative acidic or basic strength. And so pKa, we got our second dot here, is just the negative log of Ka. Pretty straightforward. pKb is the negative log of Kb. And so generally what this means is the stronger the acid, which would have a larger Ka, the smaller the pKa. And this can actually work intuitively for you if you think that pH, lower pH, is more acidic. So in this regard, it actually is in line with that rationale, where the smaller the pKa, the stronger the acid. Conversely, the stronger the base, the smaller the pKb. So let's go into a couple details of sources of protons or hydronium as we start to add some nuance to weak acids. So you have to keep in mind that there are always two sources of free protons or hydronium cation in any aqueous solution. You have the acid. Okay, so this is specific to strong acid. You have a strong acid where it nearly fully dissociates. You also have the water, because the water auto-ionizes. Now, in this particular case, the contribution of the water auto-ionizing, since it's only going to produce 1.0 times 10 to the minus 7th moles per liter of hydronium, is quite negligible in comparison to any strong acid you add. So, as you have increasing concentrations of hydronium, this is going to shift your Kw equilibrium so far to the right that the amount of hydronium produced by the water is just really going to be astonishing, very, very negligible. Because of this reason, we can, for the most part, say, except for in situations with incredibly low concentrations, that the concentration of acid in solution is due to the addition of the strong acid, or the concentration of acid in solution is due to the concentration of the strong acid being added to the water. Even though water is auto-ionizing, its contribution is just trivial to the point where it's going to be below any reasonable significant figure that we're interested in. Now, for weak acids, it's not quite as simple sometimes. You have the same situation where there are two sources of hydronium in any aqueous solution. In this case, you have this weak acid and you have the water. However, in this case, weak acids only undergo partial ionization. So it depends on how weak they are. And if they're quite weak acids, you may run into scenarios where the contribution of the water is relevant. So to remember, calculating the concentration of free protons or hydronium requires solving an equilibrium reaction, which we've been doing for a while now, a couple weeks. And this equilibrium is defined by the general equation we see here, where you have a generic weak acid, HA, plus water, is in equilibrium with the conjugate base of that weak acid, A minus, plus hydronium, where the acidic proton is reacting with the water to form hydronium, and that's leaving you with the conjugate base A minus. So if we're interested in finding the pH of a weak acid, there's just a couple steps, and this should be quite familiar because it's just another scenario, it's another application of the equilibrium problems that we've been solving. Step one, you need to write your equation for the acid and use this as a guide, and this equation for the acid should generally follow that generic equation we just looked at in the previous example, the previous slide. And then step two, you set up your ice table and then fill it in based on the given information. You need to keep in mind, you have your stoichiometry that you have to account for. Step three, substitute the expressions for the equilibrium concentrations into the K expression, which is absolutely relevant. And then 4, you determine your concentration of hydronium or free proton, depending on how you wrote the balanced equation, from your calculated value of X. So you just find your X and then you substitute it back in utilizing your stoichiometry, and you find your concentration value for your hydronium. And that's it. And you can double check your answer, which is always recommended when you have this many steps. So another way you can evaluate the strength of an acid is to look at the percent ionization. And so what percent ionization is the percent of the acid molecules that are ionized when you add them to water. So a higher percent ionization means the acid is going to be stronger because it's going to have more dissociation, where your weak acid HA is dissociated into its free proton and its conjugate base. So the more of that happens, the more protons that are being added to solution, the stronger the acid. Conversely, if you have a low percent ionization, this is going to mean you have a weaker acid. And the percent ionization is just determined by the concentration of your ionized acid divided by your initial concentration of acid times 100, or the concentration of hydronium or / free protons in solution over your initial concentration of your weak acid. And you can determine, if you can do this experimentally, your concentration of free protons in solution through the pH equation. You can take the pH of this. If you know how much acid you've added to the water, you can then take the pH. From the pH, you can convert that, pH equals negative log concentration of protons, find your concentration of protons / hydronium at equilibrium, and then divide that by your initial concentration, which you set, and then you'll know what the percent ionization is. I think this is a little redundant, so we're going to skip this one. Okay, so it can get a little bit more complex too. There are scenarios where you need to find the pH in mixtures of acids. And so for any mixture of a strong acid and a weak acid, the strong acid will completely dissociate and the weak acid will not completely dissociate. And the complete ionization of the strong acid is going to provide more than enough of these free protons to shift the weak acid's equilibrium to the left, to the point where the weak acid's contribution is negligible. And this brings up a very interesting point, which we're going to talk about more when we discuss buffers. But remember when I said at the beginning of the last lecture that acidity and basicity are relative to one another? Well, this is a really good example, because if we have, let's say we have a weak acid HA. And this weak acid is some kind of generic carboxylic acid, and its pKa is 4.8. Well, because it has a pKa of 4.8, it's acidic, because we know on the pH scale it's below 7, but it's not a strong acid. It's not a really strong acid. Now, we don't have the General's equations for this, but let's say we put this into an environment where we've added strong acid, and the strong acid has the pH of the solution at 1.8. So we have 3 units difference between the pKa of this weak acid in solution and the pH of its environment due to that strong acid that was added. Now, here's the really interesting thing about this. For this generic equation, where we have HA is in equilibrium with the free proton form and its conjugate base, it only will behave as an acid, meaning giving up its proton, when it's in an environment that's conducive to that. Remember Le Chatelier's principle? Well, because the pH is 1.8, there's this large surplus of protons floating around in solution. So what we're doing is we're adding more protons back in. And as we add more protons back in, that shifts the equilibrium back towards the reactant, which is the acid in its non-dissociated form. Meaning, the more acid we put into solution, the less this weak acid can behave as an acid. When you put in weak acid in an environment which is more acidic than it is, it struggles to act like an acid. And because of that, this weak acid, and like I said, the calculations, we'll get into this for next, is going to be 99.9% in its protonated form at this set of conditions where you have a pH difference of 3 between the pH and the pKa. And this is really important because when going back to this initial statement, when you have a weak acid in combination with a strong acid, the strong acid is going to immediately fully dissociate. This is going to shift the equilibrium of the weak acid towards its reactant, non-dissociated form, and kind of nullify its acidic behavior. And because of this, its contribution to free protons will be negligible. So generally, if you have a mixture of a weak acid and a strong acid, and you're interested in finding the pH of the mixture, you can focus on the effects of the strong acid alone, typically. So for mixtures of weak acids, though, you only need to consider the stronger of the acids for the same reasons. If there's a fairly significant difference between them in their strength based on their pKa's. If the pKa's are several units apart, you can focus on the one that's more acidic, the one that has the lower pKa or higher Ka, whichever one you're looking at. Now, bases. The stronger a base is, the more willing it is to accept a proton. And this is because, the general function of a base. A base likes to accept protons by definition. So the better a base is, the more it wants to accept that proton. So for ionic bases like sodium hydroxide, where the basic component is the hydroxide anion, this is a strong base, which means that nearly all of it is dissociated into sodium cations and hydroxide anions. So it's a strong electrolyte, just like your hydrochloric acids or your nitric acids or your sulfuric acids. And also remember that just like pH, pOH is the negative log of the concentration of hydroxide. So weak bases, only a small fraction, just like the difference between a strong acid and a strong and a weak acid, the difference between a strong base where it fully dissociates and a weak base is that in the case of a weak base, only a small fraction of your molecules are available to accept hydroxide. So whereas, free protons. So as we're in a case of a strong base where you have hydroxide and then you have hydronium, this nearly completely goes to the base accepting the proton off the hydronium and forming a unit of water, and then leaves the water behind, so you actually get 2 units of water for this reaction. Now, this can also be drawn as hydroxide, and I should have aqueous for this, plus your aqueous protons form water in liquid form. This is your strong base, strong acid type interaction. In the case of weak bases, you don't have a one-to-one scavenging effect on these free protons. And this is a really nice example with ammonia, where ammonia, remember, has this trigonal structure with a lone pair, and this lone pair is able to accept a proton and become ammonium cation. So, but only does this a little bit. It doesn't do it comprehensively. So not every unit of ammonia in solution will scavenge free protons to form ammonium unless there's a very, very large excess of free protons available, which force the reaction. So in this particular case, I think it's important to remember that the amount of hydroxide produced is much lower in this particular case, and however, don't make this confound you too much, because finding the pH of a weak base solution is almost identical conceptually to finding the pH of a weak acid. Now, another thing to consider with this is we keep talking about concentration of hydroxide, right? Well, how is hydroxide formed by a weak base if it likes to scavenge protons? Well, in this particular case, let's take a look at ammonia. Let's say we have our ammonia, and it has, and we're going to put this in aqueous solution, and then we add it to water. Well, in this particular case, what's going to happen is, let's look at this picture of ammonia over here. And once again, I'm not going to make you guys draw this, but let's say we've got our ammonia and our water. What's going to happen is the ammonia is going to act as our base, and the water is going to act as our acid, because it's amphiprotic. And this lone pair is going to grab that unit of that hydrogen, and it's going to break the bond between the hydrogen and the oxygen, pushing those electrons over to that oxygen. And what's going to happen is you count OH minus, this will become, the ammonia will become ammonium with 1, 2, 3, 4 protons, and the water will become hydroxide. And so for every time ammonia scavenges a proton off of water, we're actually producing hydroxide, which is where we can find our POH. So that leads us into, so this F function should be an equilibrium. Translation error from copying and pasting. So remember, base ionization constant is Kb, whereas for acid ionization it was Ka. Just like we have pKa, we can have pKb as well through negative log of Kb. The base constant, remember, base strength is measured by the size of the equilibrium constant when it reacts with water. So that reaction I just showed you with ammonia specifically, base plus water will form the protonated or conjugate acid version of that base plus hydroxide. So the equilibrium constant of this reaction is Kb. And that's just going to be an expression of your products over your reactants. And in this case, of course, water falls out because it's a liquid, so we're not including it. So only the concentration of your hydroxides and your conjugate acid over the concentration of your weak base matter. A couple weak bases we should be comfortable with. Ammonia, obviously. Carbonate and bicarbonate, classics. Just, you don't need to know the kBs off the top of your head, but you should know when you read bicarbonate, carbonate, ammonia, pyridine, methylamine, that these are basic compounds because they pop up over and over and over again, particularly carbonate, bicarbonate, and ammonia, and pyridine. So how do we find the concentration of hydroxide and pH of weak bases? Well, it's very similar to weak acids. First, step one, write your equation for the acid and use the guide to prepare your table. And then you just fill out your ice table like you would normally, keeping in mind your stoichiometry, of course. And then you need to substitute the expression for your equilibrium concentrations into K. I think this is almost identical, actually. And then you determine your concentration of hydroxide from the calculated value of X. So whatever X was, fills in for your concentration of hydroxide, and then you just find your pOH as necessary. And from pOH, you can determine pH, because it's just 14 minus pOH. And that's it. Straightforward. And during the recitation, I'll run some examples. There's also really good examples on the e-text, which I'd strongly recommend you just watching the video to get you started. So let's talk a little bit about acid-base properties of ions and salts, because this is actually pretty important. So salts are, by definition, ionic compounds, and so not all salts are soluble, but soluble salts form ions in solution. So instead of just having their ionic bonds forming in a lattice, when you put them in water, the water hydrates them and separates them into their individual anions and cations until the solution gets saturated. So the cation of a strong base and the anion of strong acid do not ionize in water. Therefore, they don't affect pH at all. However, the cation of a weak base and the anion of a weak acid will ionize in water, and this affects the pH of solution. So let's take a look at this. So you have sodium, let me jump back up in here real fast, get oriented. Good. Okay, making sure I didn't skip something. We have sodium bicarbonate solution, and it's going to be basic. So the sodium is the cation of a strong base, right? Sodium hydroxide. So it's going to fully dissociate, not interact. And the bicarb is the conjugate base of the weak acid, H2CO3, because notice that if we added a proton, that would make it a conjugate acid to that base, or this conjugate base of the weak acid. Either way is appropriate. It's important to just recognize the generalities that anions tend to form basic or neutral solutions because they have extra electrons that can act generally as bases, and cations tend to form acidic or neutral solutions because they're typically doing the opposite of that. So let's look at the anions as weak bases first. Pretty much every anion can be thought as the conjugate base of an acid. So for the example, you have this conjugate base, A minus, in aqueous solution in water is in equilibrium with the constant, with your weak acid and your hydroxide. In this particular case, this base, which is your conjugate base to your weak acid HA, comes over here, it grabs this proton off of the water, liberating a unit of hydroxide and putting one of those hydrogens on, forming the weak acid. So the stronger the acid, the weaker the conjugate base. This is really important. The stronger this is, the weaker this is. And let's rationalize that really fast. If this is a great acid, that means it's really good at giving up its proton. If it's really good at giving up its proton, that means that that conjugate base, A minus, doesn't want the proton back. If it doesn't want the proton back, that means it's not a very good base, right? So the better this acid is, the weaker the conjugate base is. Conversely, if A minus is a strong base, and it really wants to take protons off of things, like water, its conjugate acid, HA, is not going to be a very good acid. Because if A really wants that proton, it's going to hang on to it, right? It's not going to want to give it up in its acid form because it's happy now. It's got its proton and it's satisfied. So remember, the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. And you see this trend here where you have your strong acids with acid strength increasing over here on the left side, and you have the basic strength increasing going downward on our right side. So when you're looking at your strong acids, your hydrochloric acid, your sulfuric, your nitric acid, etc., the conjugate bases for these are the chloride, the HSO4 minus, the NO3 minus. These are not good bases. They're actually neutral because the strong acids fully dissociate. Those conjugate bases don't want those protons. So they're very, very poor bases to the point of where we can define them as neutral. Conversely, let's look at something in the middle here. Let's look at hydrofluoric acid. Hydrofluoric acid has a weak or intermediate base. So it's still a pretty strong acid. It's in, fairly low pKa, but that means because it's still a fairly strong acid, its counter ion, its conjugate base, is a poor base still. It's basic, but it's only weakly basic. And then if we were to look at, say, ammonium, we know ammonia is a reasonably weak, strong, remember, strong and weak in terms of bases is relative, right? So it's not a strong base, but ammonia is a decently strong base. And ammonia is the conjugate base to ammonium. Well, this trend basically carries right through. So let's look at this relationship between the Ka of an acid and the Kb of its conjugate base. I think this is just going to be a proof of concept. Many reference books only give Ka tables. So if you're looking for Kb's in tables, you're not typically going to find it, because the Ka defines the Kb fundamentally through Kw. So remember, Ka times Kb equals Kw, or concentration of free protons slash hydronium times the concentration of hydroxide also equals Kw. So you have an interface between these three relationships that makes finding one from the other incredibly simple. And this is a little redundant because I already described it on the previous slide, but remember, just as we saw before, the stronger the base, the weaker the conjugate acid. So the stronger the acid, the weaker the conjugate base, the stronger the base, the weaker the conjugate acid. Anytime you have a strong base, a true strong base, which is a strong electrolyte that fully dissociates, its cation is going to be neutral. And if you have a weak base, the cation, which is the conjugate acid, is going to be just weakly acidic. And so this is another, we actually did the ammonium as an example, but let's revisit it. So in the case of ammonium in water, it will act as an acid. The acid, one of these protons, will be liberated as water acts as a base, abstracting that proton from the ammonium. This will give you ammonia and the conjugate base to conjugate acid to the water, hydronium. So, important point here, if you were breaking this down for somebody, describing conjugates, this would be our one of our acids. This would be the conjugate base to that acid. This would be the base for our reaction as drawn on the side of our reactants, and this would be the conjugate acid to that base. So it's worth pointing out that metal cations can behave as weak acids. So cations of small and highly charged metals do behave as acids, albeit weak acids. And alkali metals are called, and alkali earth metals are specifically neutral, but cations are hydrated. So let's take a look at aluminum, because aluminum 3+, if you put it in water, is going to get surrounded by 6 water molecules. So what's going to happen here is, let me draw this a little bit. You don't get necessarily bonds like the book's showing you here. What's happening is you have your aluminum, which has a +3 charge distributed around the entire thing. What happens is water has, remember, these partial positive and partial negative charges, where, excuse me, I drew these arrows completely backwards. The electrons tend towards the electronegative oxygen, so you get this partial positive charges on the hydrogens, and you get a partial negative charge on the oxygen. So what you see here is the red globe oxygen side has this zone of partial negative charge, and you have 3 full units of charge on the aluminum. So 6 of these waters, oxygen sides, come in with their partial negative charges, and this helps neutralize the positive charge of the aluminum. And so this is what hydration of a metal looks like, is the interaction of metal cations in water, with water providing semi-stable structures surrounding these metals. Now, because of this, let me erase this for us. Get rid of that too. It's not that hard for one of these waters, which are, I'll use the word bound loosely, bound to the aluminum, to give up one of its protons to another unit of water, and this will form an OH 2+ over here. Excuse me, the 2+ is for the entire complex, but it'll form an OH over here and an H3O+ or hydronium here, which is an equivalent of acid. So because of this hydration effect, you can actually get these hydrated cations acting as bases, as acids, and forming hydronium in solution. And this is pretty much a restatement of what we've already gone through, so I'm going to let you guys read through that if you need it, but I don't think we need to lean on it too strongly. And same for this. Okay, and this is all 3 parts of things we've already discussed. Cool. Okay, so let's talk about polyprotic acids a little bit. So everything we've been doing so far has been relatively simple, where we had a single proton, which was acidic, that we were interested in. However, some acids have multiple acidic protons. And because of them having different acidic protons, each of those acidic protons has different relative acidities. They don't all come off at the same time, and most of the time, the first one will be a strong or weak acid, and then everything after that will be a subsequently weaker acid. So, like it says here, polyprotic acids ionize in steps with each proton having a different Ka, and Ka1, Ka2, and Ka3 are defined inherently by which one's the strongest, with Ka1 being the strongest, and it will leave first, Ka2, second strongest, it will leave second, etc. Typically, the difference between the Ka values is large enough so that you don't have to worry about the second ionization, because for the same scenario that having different acids in solution changes the equilibrium for the stronger acid changes the equilibrium for the weaker acid due to Le Chatelier's principle. The same is true for polyprotic acids, where the pKa's are fairly separate, where you have 1 or 2 pKa units between them, or the Ka is just substantially larger. Ka1 is substantially larger than Ka2. There are scenarios where the pKa's or Ka's are fairly similar and they actually affect one another, and that's quite complex. And I'm not going to test you on that scenario because that's for a later class, but you should be aware of it. Citric acid is a good example of one where you have 3 different carboxylate ions on a single compound, and they're fairly similar in terms of their pKa values. And so that's a very complex polyprotic acid. But I won't ask you any questions related to citric acid because of that. A few common polyprotic acids you should be aware of. Sulfuric acid is a classic. And remember, sulfuric acid, the first proton is actually a strong acid, and it fully dissociates. The second proton is relatively acidic, but not a strong acid. And in that particular case, by definition, if you were interested in the acidity, you would look at the concentration based on the effect of the strong acid exclusively, because the production of free protons from the strong acid effect of the first proton will substantially drive the equilibrium of the second towards the reactant side, meaning it won't dissociate significantly. Other ones include oxalic acid, sulfuric acid, and phosphoric acid. Phosphoric acid in particular is a really common one we see in biochemistry and biological solutions. We also have citric acid. This is the one I just described. Notice how similar the pKa's are, particularly these first two. And because of that, these two actually do affect one another, and I won't be asking you questions regarding citric acid. If you get a question in another class regarding citric acid and its dissociations and you're doing pH adjustments, be aware that this is actually a substantially more complex problem. And this may be redundant from what we've already discussed, but let's look at it. So let's look at the ionization of sulfuric acid specifically. So ionization constant for your H2SO4 are as follows. The first one is strong. So you have your sulfuric acid and water here, and this is going to pull your first acidic proton off through dissociation. It will interact with the water. The water will act as our base, and we will get HSO4- as a conjugate base to our strong acid, and hydronium cation as our conjugate acid to our base water. Now, we still have HSO4-, which is acidic, albeit a weak acid. So HSO4- plus water is in equilibrium, forming SO4-2- plus your hydronium. And this is going to have a Ka2 of 1.2 times 10 to the minus 2. Now this, like I said, is going to be saying it's significant because it's 10 to the minus 2. So it says, for most sulfuric acid solutions, the second ionization is significant and must be accounted for. That depends on the degree of accuracy you're hoping to get. But if you are interested in calculating the acidity due to the contribution of both protons, you know that H2SO4 will fully dissociate due to being a strong acid, meaning the concentration of H2SO4 will also equal the concentration initially of our HSO4 minus, and will also equal the initial concentration of your hydronium initially, which would make setting up an ice table really straightforward. So here's the walkthrough on that. What you would do is you'd write your equation for each proton that you need to count for its ionization and use them as a guide for preparing your ice table. We're definitely going to have to run one of these examples in the recitation. Complete the first ice table based on the given information. Substitute your expressions, your equilibrium concentrations into your K expression. Complete the next ice table based on the information calculated from the first ice table. So you're having an ice table on top of an ice table. Now, this gets kind of substituted if you have a strong acid, like in your case of your sulfuric. You don't need an ice table for the first one because you know what it is from its full dissociation. So you can skip right to step 4 if you're dealing with sulfuric acid, and then you determine your concentration of hydronium from the calculated value of X, and then you can calculate pH or pOH as necessary depending on what the question's asking. Let me pause real fast. So let's get away from ice tables for a minute and discuss how you might intuit the relative acidity of a binary or oxyacid. Looking at its structure. Let's say you don't have the tables for the Kas or the pKs available, and you're interested in the strength of something based on its structure. These are some trends you can use as general guides to make comparisons between compounds to determine which is likely most acidic or less acidic. And for the strength of binary acids, it's relatively straightforward to make the determination, because the more polarized the bond is, the more acidic it likely is. So specifically the bond between your central atom and your acidic proton. So that's what we're looking at here, where the bond between the central atom Y to the proton is highly polar. And the more polar it is, the more the electrons get pulled towards the central atom Y, and the more tightly the central atom already owns those electrons, the easier it is to just let go of the proton. And the easier it is to let go of the proton, the easier it is for that proton to behave as an acid. Conversely, the stronger the bond is between the central atom and the acidic proton, the weaker the acid will be, for the exact same rationale. If you have a really strong bond between a proton and a central atom, that bond is strong because it's low energy, it's happy, it's stable, and it doesn't want to give that up by giving up that proton for it to act as an acid. So if you're looking at something like methane, methane has carbon in the center and 4 hydrogens. It's very, very happy. All those bonds are very happy, therefore very strong bonds, therefore not acidic protons. So typically, binary acid strengths increase as you go across a period to the right. And this is a really good example here, where if you're moving across periodic table this way, you're going to be increasing in acidity because you're going to be increasing the polarization of the bonds. Also, binary acid strength tends to increase as you go down a column. And this is because as you go down a column, the bond lengths increase because the electrons are held more distantly from your central atom, and that makes them less stable bonds inherently. So they're going to be inherently slightly weaker bonds, which will make them better acids. In the case of oxyacids, where you have a scenario like this, where you have an acid bound to this oxygenated central atom, the more electronegative your central atom Y, the stronger the acid, or in this case, the oxyacid. And this is going to be a good explanation as to why the acid with the chlorine is going to be stronger than the acid with the iodine. So the acidity of your oxyacids are going to decrease as you go down in groups, just like in binary acids, because this helps weaken the bond between the hydrogen and the oxygen. Also, the larger the oxidation number of your central atom, the stronger the oxyacid will be. That's a general trend. And because of this, the acidity of your oxyacids tend to increase as you go from left to right across a period. And this is opposite trend of your binary acids. And lastly, the more oxygens you attach to your central atom, the stronger the oxyacid. So if you see some central atom and it's got 3 oxygens bound to it, that's going to make for a pretty strong oxyacid compared to one where you only have 1 oxygen bound to it. Good example here on the very bottom. These are just, here we go. This is a good example for that last step where you have 4, 3, 2, and 1 oxygens respectively. All the central atoms are chlorines, so you don't have a difference in its electronegativity. But the difference is the number of oxygens bound to it, where with 4 oxygens, it's a strong acid. With 3, the Ka is 1, also pretty darn strong acid, but not true in terms of full dissociation strong. 2 oxygens losing its acidity, 1 oxygen not particularly acidic. Last thing to add for the chapter before we call it a wrap for chapter 17. We've talked about 2 models of acidity, and we're going to add a third. And the third model of acidity we want to address is the Lewis acid-base theory. So Lewis acid-base theory, unlike before where we focused on whether or not an acid makes a proton in solution, or a base makes a hydroxide, or the second theory, where an acid donates a proton and a base accepts a proton. In the case of Lewis acid-base theory, Lewis focuses entirely on the electrons. So Lewis acid, by definition, is a lone pair acceptor, and a Lewis base is a lone pair donor. And the reason this is particularly relevant is because we don't need protons to define acids and bases in this case. Now, a proton can act as a lone pair acceptor, so it meets the criteria for a Lewis acid base just fine. But it doesn't have to be a proton, and we're going to get a couple examples of those cases. So notice, oh, well, here we go. Let's move down. So Lewis acids. Lewis acids are inherently electron deficient. That makes them eligible to accept a lone pair. And this can be either from being attached to electronegative atoms or just not having an octet. And we know of a couple examples like BF3, where from Chem 105, where it doesn't have a true octet. So that makes them Lewis acids because they're happy to take on a lone pair of electrons. They need to have an empty orbital so they have room to accept a lone pair. That's another really important criteria, because if they don't have available orbitals, they can't just take on extra electrons someplace. Now, it's good to note that your proton has an empty 1s orbital because it lost its single electron, and it has room for a pair of electrons in that orbital. Conversely, or as a second example, the boron in BF3 has an empty 2p orbital because it has an incomplete octet. So either through charging or through having electron deficiency from having a highly electronegative atom attached to it, or having an incomplete octet, these conditions have to be met for it to be a Lewis acid. So generally, what's that look like? Well, lots of small, highly charged metal cations have empty orbitals, and they can accept electrons just fine, and that makes them reasonable Lewis acids. Also, atoms that are attached to highly electronegative atoms and have multiple bonds can be Lewis acids. So let's look at some of these. Or excuse me, let's look at Lewis bases, and then we'll look at some examples. So Lewis bases, a Lewis base has to have electrons it's willing to give away to another atom, and almost exclusively in the form of lone pairs. So we're really looking for lone pairs of electrons that it can donate as a base. Anions are typically better Lewis bases because they carry that charge, and that charge, because it's not neutral, makes that species prone to want to give up some electrons to reach neutrality. Because of that, a nitrogen with a lone pair and a charge is going to be a superior Lewis base to a nitrogen with just a lone pair. Also, generally, the more electronegative an atom is, the less willing it will be to be a Lewis base, because the more electronegative it is, the more it wants to hold on to its electrons, or the more comfortable it is stabilizing that electrical charge from that lone pair. So sulfur, because it's a more electronegative atom, excuse me, I got this flipped. Oxygen is more electronegative than sulfur. Therefore, sulfur will want to give up its lone pair more. Therefore, it will be a stronger Lewis base. So, Lewis acid-base reactions. This takes place through the form of adducts. And we're not going to spend a lot of time looking at it, but this is through the transfer of electrons in the form of an adduct. And please remember, Arrhenius and Bronsted-Lowry acid-base reactions are also inherently Lewis acids and bases. So when we're talking about adducts, this is a great example. We have an aluminum with 3 chlorines bound to it, and it has, and we're going to add ammonia. So we have an aluminum, which is your small metal, and then we've got our lone pair here, and we can form an adduct and make everything happy. And now we have an octet around our aluminum, whereas we did not before. And we have BCl3, same scenario, where we are deficient in electrons around the boron, and we have a couple lone pairs hanging out here on our diethyl ether, and that can form an adduct to get a Lewis acid-base reaction. And that is all for chapter 17. So we covered a whole lot of material here, and you'll note when you're in the homework, there's a lot of homework problems, because I need to assign enough problems that you have the ability to establish comfort within all of these. Now, the good news is that a lot of these aren't very computationally heavy. They're more conceptual, and conceptual ones happen faster, but we have to work through enough scenarios where you establish an intuitive comfort with the material without referencing something to get your answer. So go ahead and jump in. Please get started with it if you already haven't, and really start chipping away at it aggressively so that you have the time and latitude to revisit it and study it and get genuinely comfortable with it. Because chapter 18, when we get into buffered systems, is going to lean very heavily on the concepts from this particular chapter, and we want to have these ingrained so that we can be successful in chapter 18. All right, that's all, and I'll be putting together a recitation video for everybody in the coming days, and I look forward to talking to you soon.